theory proof for you guys involving the GCD. In fact, sometimes you see GCD prepended. I just write it like this as an ordered pair, so to speak, but often you see GCD in front of this just to remove any ambiguity for it being an ordered pair. But this is also sometimes called the highest common factor. But we're given A, B distinct integers, and so that, of course, means A does not equal to B. Now, we're supposed to show that there are an infinite number of positive integers in such that this GCD statement holds, okay? And notice the GCD, the first element of the GCD is A plus N, and the second one is B plus N. And we want to show that there's an infinite number of positive N's such that these two guys are relatively prime. Now, there's a lemma here that I'm not going to prove. It's a kind of a technical proof. It's more or less equivalent to the Euclidian algorithm where you keep dividing a pair of integers and you get a sequence of remainders that are pairwise relatively prime. It's more or less based on that, sort of, you know. But anyway, let's just do a concrete example of what this lemma is, because we're going to do it repeatedly. Now, so let's just take a look at the GCD of, let's say, something we already know the answer to. 51 and 9, okay? And we're going to apply this lemma. Now, a lot of you already see the answer to this. This is 3 squared, and this is 3 times 17. So we know the answer to this. But let's take a look and see how this works. According to the lemma, we can take a multiple, any multiple of 9, and subtract it from 51 and get an equivalent GCD statement. So I'm going to do 9 times 5, which is 45, and subtract it from 51, and that would give us 6. So now we have 6, 9. Right, folks? See, and again, I just applied this thing twice. I took 9 times 5 is 45, and you deduct 45 from 51, and you get 6, 9. Now, a lot of you go, okay, I can see the answer right now, but this goes, it doesn't just work this way. It could be X that's isolated and Y that we're subtracting multiples from, okay? So if you do that, you can actually subtract, and again, we're done with the problem. We were done with it right here, but I just want to show you how this lemma works. You can subtract just one multiple of 6, namely 6, from 9, and you get that this is equal to 6, 3. All right. If you want to go nuts with this, you would actually get that this is equal to 0, 3. In the old number theory, authors would do this. Okay. And of course, 0 is a multiple of anything, right? So this is equal to 3 manifestly. Okay. So again, y'all, this is overkill because you know the answer to this from the beginning, but this lemma is going to be super helpful to help us construct an N here. Okay, now let's go ahead and we can, the usual without loss of generality, we can assume A is greater than B. And we construct this N more or less based on this idea here, even though I'm not going to go to too much trouble to motivate it. You can see that it works once there's a lot of discovery when I was working on this, and I'm not showing you any of the discovery. But anyway, we're going to choose N to be A minus B, where A minus B would be a positive number, right? Since we're assuming in other words, A minus B is greater than 0, right? Now, so let's check this out using this lemma. Now, here's our original problem. Now, we've chosen N to be this, y'all. And by the way, you would have to choose M to be big enough to where this would be positive, right? Remember, we want N to be positive. So it may be the case that B is really it'd be a big enough number to make this whole thing negative, but we can choose an M big enough to make N positive, right? We can choose M big enough to make N greater than 0, right? And again, I won't say anything else about that, okay? So here we go with the substitution. Now, y'all notice that all I'm going to do is apply this lemma twice, okay? Okay, so you can see what happened right here. Right here, I just literally subtracted this part from this right over here, okay? Okay, and you can see, folks, that we get this statement right here. Okay, we get this statement right here. In other words, here a minus b m plus 1 got subtracted away from this, and that just left a minus b, and this remains unaltered, right? See how that works? So that's kind of cool. That's one application of our lemma up here, okay? Going from this line to this line is one application of the lemma. Now what about right here? Okay, well, now we multiplied this by m, right? And subtracted it from this, you see, but that makes the a minus b m go away, right? Isn't that cool? So two applications of our lemma here leads to this very easy to discern result. Okay, if one is certainly the GCD, if one is one of the operands, if you want to call it that. So we can write QED here. Well, it's a little melodramatic to call it QED, but we have shown that an n in this form, and again, I apologize, it would take an extra 10 minutes to go through the discovery on this. You play around with some numbers, and you can see that this works, but you can see that it fits this also, which is kind of interesting, and it takes some time. It's not nearly as quick. At least for me, it took me quite a while, like over an hour or two, to really get into this problem and know how to select our n. And you could do it either way, I guess. You could you could have your a here, and you could it's symmetrical sort of expression. Okay, so it's nothing special about doing it for these in this way. You could have a minus a here, and then these variables would be swapped, I guess, you know. But anyway, I just think it's kind of cool how you can just physically work with there's no numbers here, and you're applying this result that's normally reserved for just known numerical instances to more, shall we call them, abstract expressions. But anyway, this particular n, since there's an infinite number of m large enough to make n positive, that means there's going to be an infinite number of n, and we've just shown you that n in this form leads to a GCD of 1 for our original expression. Okay.